All right, welcome back to the afternoon session. So we are going to start again with our 10th lecture by Danielle Berg.
All right, thank you very much. Good afternoon. I remember I did a winter school when I was a graduate student in the Canary Islands, and Daniela Calzetti, I don't know if you know that name, but she was the lecturer right after lunch. And I remember I was always so tired and my belly was full and it was hard. And she would come in right after lunch and wake me up. So I just want you to take a second and just take a deep breath in, fill your lungs with oxygen so we can be awake, get through this together. We'll do our best. My name is Danielle Berg. I like to introduce myself as a neurodivergent, bisexual assistant professor at UT Austin. And I like to start that way because I like to open myself to you that way in case you are someone that is looking for a friend, ally in those spaces, or if you're someone that has questions or uncertainties about what those things mean in astronomy or ways you can better show up for people around you and in your groups, I'd love to chat with you. So I just wanted to start with that because we all do better science when we all do better science and when we all feel included. I'm going to talk to you today about what was originally invited to be the UV visible ISM and galaxy studies, but I'm going to extend it to the mid-infrared because I think that's really important in today's JWST era. My goals for this lecture, here we go, there we go, are to talk to you about how to understand the spectroscopy that we see and how we use it to probe the interstellar medium in galaxies, their conditions, their abundances, the things that they're telling us. Describe key diagnostics of chemical abundances, depletions, dust attenuation. We'll talk a little bit about how we've done that in an integrated sense, but now we're really opening, a new era where integral field units like MUs are really telling us about resolved properties in galaxies. And then kind of understand where we're at today. What are the current limitations and how we're really going to move things forward with future observatory synergies. And I think really having multiple IFUs in different wavelength regimes is going to be really, really powerful. Now I'm going to start the next part of the lecture with some interstellar medium basics from the things that I study, because I wanted to get a sense of what others were talking about over these 2 weeks. And so far, the topics I'm going to do, I don't think have been covered extensively. And talking to many of you, you don't necessarily study what I study. So I want to make sure we're all on the same page. And if you already know some of this, then you'll just feel really smart for the next period of time. So going to the very beginning of why I like to study the chemical abundances of galaxies, particularly from ionized gas in star-forming regions, is because we know that at the beginning of the universe, there were no metals, things heavier than hydrogen and helium. Those were made in stars. So if we start with pristine gas and we form our first stars, they create heavier elements in them. They blow up and disperse those into the gas. So we now have a more metal-rich gas. The subsequent generation of stars that form now have those metals in them. They create more metals. They blow up, again, putting them into the gas. And so we get this really simple building up of metals over time, such that when I measure how many metals are in a galaxy, it's kind of like looking back at its history. Sometimes I like to think of it as like looking at, a family tree. Can like study all the characteristics of all the grandchildren today. I might learn something about where they came from originally. Of course, the picture isn't this simple in reality. This is a complex, messy-looking thing that is from the Starforge simulation. And in particular, things don't happen in a closed box. So we also know that we get low metallicity gas that accretes onto our galaxies. We know that we get energetic outflows from things, sometimes feedback from EGNs, sometimes from our supernovae that drive metals out of galaxies, that regulate the star formation. Sometimes we get mergers. We get all sorts of messy things that cause us to be a little bit more complicated that we need to study in more detail. But in that way, those also leave an imprint on the chemical abundance signature that we see, and so help us understand what's happened in total. Now, when we look at things that are really nearby, we can actually even see the individual stars, and we can see the gas that they formed from, the molecular gas. We can see the ionized gas that they're ionizing directly around these stars. And so we get this really beautiful picture that we can study in detail. From that ionized gas, we get a couple of things. Interesting. Okay, I was like, it changed on my computer. Okay, so we get recombination and photoionization. So photoionization just means those energetic photons that are more energetic than 13.6 electron volts. They can ionize hydrogen. And the way that we look at our volumetric photoionization rate is we care about how much density of neutral hydrogen we have. We have some rate of ionizing photons. And if we expand that a little further, we might care about the cross section of how likely those photons are to actually hit our hydrogen. So if we do something like assume an O star that has 10 to the 49 photons per second per centimeter squared, and you have a typical cross section of 10 to the minus 18, and you look at a certain distance from your star, you can actually take this rate and invert it, and to get a photonization time. And you see that we photoionize our gas really quickly. Okay, so we can photoionize on the order of hours. Whereas if we look at how long it then takes those electrons that are running around to recombine with our protons, the ionized hydrogen, we have a slightly different equation. So we have our density of electrons, our density of protons, and we have this total recombination coefficient. And so we can put in some assumptions. Our recombination coefficient is going to depend on the temperature of our gas. So if we have a typical ionized gas temperature of 10 to the 4th Kelvin, a typical nearby ionized density of 100 electrons per cubic centimeter, and this is a case B total recombination coefficient, a typical value, then we can, again, invert kind of what we're looking at for a time instead of per volume, but the rate, 1 over the rate will give us a time. And we see that it takes a lot longer for everything to recombine. Now we're looking at something like 10,000 years. So this is just important to note because even after our stars turn off, if you will, or the most massive stars blow up, we're still going to see this ionized gas hanging out for a while because it takes a while to recombine. Okay. So I like to study these ionized regions, and I like to study them in all wavelengths, really, but I've spent the majority of my time studying them in the rest-frame ultraviolet, optical, and mid-infrared. Well, why do we do that? Well, these different ranges give us really important properties that we can study. But one of the things that we've done historically is we started by observing galaxies nearby us in the optical, because we could do that from the ground. Our atmosphere lets us do that. Then we built space-based telescopes to start to observe them in the ultraviolet and in the infrared. But when we want to start looking back in time and piecing together the total evolution of galaxies, their chemical histories over cosmic time, these same spectra are going to redshift, so that we observe them in different bands. Now we can do the UV of redshift 2 to 3 galaxies from the ground with those same optical telescopes. But if we want to observe their rest-frame optical, we might need space-based telescopes to observe them in the infrared. And then they redshift even further when we get into high redshift regime, which I call greater than 6. Other people call other things. But this is still local to me. This is still intermediate redshifts, and this is still high to me. And so then we need to use something like JWST to go into the infrared. But one of the things that I've really loved is people are like, why do you study the UV? Well, I can study that same spectra regime across all of cosmic history if I use things like Hubble nearby, ground-based for the intermediate redshifts, and JWST for the high redshifts. I can now directly compare all the same tracers, so that's really amazing. As I said, these trace different portions of gas. So just to give you some idea, if these are our different rest frame bands, these are some of the important emission lines, UV emission lines that we might look at, some of the important optical emission lines we might look at, or this is the Lyman limit, 912, where we hit our edge for ionizing photons. You can see how they evolve across wavelengths into different regimes where we might want to observe them. And we do actually want to observe all of them, which sometimes becomes challenging because we might get things like molecular gas, our warm H2 in the mid-infrared. Sometimes you can get those in the extreme UV as well. I'm not going to talk about that today. We get some nice neutral gas tracers, such as the Lyman series in the far ultraviolet. And we get a lot of ionized gas tracers from the far UV, the optical, the mid-infrared. And then dust is also something we study as well. We study the effects on how it attenuates the UV and the optical. So we will study that like from the stars in the UV and from the hydrogen emission lines in the optical. And then the mid-infrared, we might directly see emission from pH features from dust features. And so, or the overall shape might be reprocessed light from dust. So this is a really powerful way to study all these components. Okay, so how do we make metallicity measurements? This is a face on Spiral Galaxy, M51, has lots of beautiful components and ionized gas. And if I take a little ionized region and I take a spectrum of it, there are a couple of different ways that people measure metallicities. And unfortunately, they all are different and they use different abundances and different techniques and have different shortfalls. And so sometimes I like to say that we're comparing, a whole basket of fruit. We're not comparing apples to apples. So if neutral gas abundances, where I'm getting low ionization and neutral absorption features from things that we call them, they trace the neutral gas because they trace neutral hydrogen, but things like carbon-2 will be really low ionization and be in the same ionization zone as neutral hydrogen. We get all these absorption features that we can measure to get things like carbon, sulfur, silicon, and iron abundances from neutral gas along the line of sight. We also, as I've been talking about, get these ionized gas emission lines, but they also come in both, two types of fruit. We'll say limes and lemons, where we directly measure the number of ions in a gas, which I'll talk about, or we use strong lines, really strong lines that have been correlated with abundances to try to predict a whole host of abundances. We sometimes try to do magnesium and iron as well, but they're really challenging to do because they have require a lot of corrections. And then we sometimes try to do individual star abundances, like blue and red supergiants. Again, this is going to be absorption lines, but directly from those stellar atmospheres. And here you fit an overall abundance template or pattern to that star to understand what its composition is overall, as opposed to measuring individual elements. And so here we have bell peppers, okay, that I'm throwing in there. That's all that Keynote gave me for fruits or vegetables, so that's what I had to work with. What do these spectra look like? Okay, well, in the ultraviolet, we get a whole host of beautiful features, if you aren't used to looking at these kinds of spectra, that are rich with diagnostics. So first, the things that produce these emission lines are the massive stars, the young massive stars, and detailed features. So we have things like stellar winds, and you notice they have this kind of squiggly pattern, this P Cygni absorption to emission pattern in each one of them. You get this little squiggle here. Those are our wind features. And then we also get detailed photospheric features. Those are much smaller. And then the ISM absorption lines I was talking about, again, this is gas in the galaxy that you're observing, but in front of the stars along the line of sight. So you observe those different elements in absorption. And then you get a bunch of nebular emission lines. So you can see some of them here. We have helium-2, oxygen-3, silicon-3, and carbon-3 emission lines. We can then put those together with a different set of diagnostics in the optical. So in the optical, we have a couple of different kinds of emission lines, which I'll talk a bit more about in a moment. But our recombination lines are nice. They give us a more direct probe of the metallicity sometimes, but they're really faint for the metals. So you see the big bright ones, those are your hydrogen recombination lines. You get helium recombinations that are really bright. But if I want to see things like oxygen in recombination lines, those are going to be about 1/1000th of the strength of H beta. So unless you have really deep spectra, you're not, and high enough resolution, you see there's a lot of them right there, you're not going to measure these. So this is typically done for only galaxies within like the nearest 10 megaparsecs. Then we have all of these big, beautiful, collisionally excited lines. And so these are our metal lines that are much, much stronger. Some of them are still relatively faint, like this temperature-sensitive line 4363 here, which is about 1/100th of H beta on average, but it's still 10 times stronger than your recombination line. And then the much stronger ones that you're used to hearing about. There is some nebular continuum features, such as your Balmer jumps, these little jumps in the continuum. And sometimes, if you have older stellar populations, you might see some absorption features. Okay, and then finally, in the mid-infrared, what's really fun about the mid-infrared is we get, again, different features. We directly observe some of these polycyclic aromatic hydrocarbon pH features types of dust. We get some of these warm molecular hydrogen lines. And then we also get some of those collisionally excited nebular lines. But what's really fun here is I would mention ions here that you do not observe in the UV or the optical. And so they kind of allow us to better complete our picture of a given element. So in particular, argon 2, that is the only strong line for argon 2 is in the mid-infrared. Argon 5 is not really shown in this one, but that can be a nice one to see here. Sulfur 4 has a really weak transition in the UV, but it's stronger in the mid-infrared, which is nice. Neon 2, beautiful booming line. We only really see that in the mid-infrared. O4 also has a really weak feature in the UV, but it's much stronger here. So this gives us a better way to complete everything. Okay. And so the other thing I want you to take away when you're looking at spectra is that they visibly just start to look different if we're looking at different types of galaxies. So in particular, this one is an ultraviolet spectra from a survey called Galaxies that I'll tell you more about later. But you notice that its continuum overall looks pretty flat. There's not much for absorption features in this spectrum, but it does have a lot of good emission lines. And this is a low metallicity galaxy. It has, hotter temperatures, low metals, and so you're mostly seeing nebular emission in this UV spectrum. If I show you a more metal-rich spectrum instead, you're going to see something completely different. Now a lot of our strong emission lines tend to go away, and we start to see a lot of these ISM absorption features. We start to see these P Cygni wind features. We start to see a lot more absorption in both our stellar components and our gas components due to the more metal-rich environment. And then the other thing we've had to start thinking about lately is looking at more extreme conditions. And I know Emma gave you a little bit of a primer on this, talking about what we're seeing at high redshift, because it's starting to change the way we calculate things. But we also have to start thinking about, for instance, what the underlying continuum is and how that changes diagnostics that a lot of people use, like equivalent widths. Or if we're fitting an overall, some of you have talked about doing your spectral energy distribution fitting, your SED fitting. You need to know what the overall shape is. And so the overall continuum that you're seeing here is this dark purple line, and it's showing you what it looks like if you only have a low density of 100 electrons per cubic centimeter versus if you have 1,000,000 per cubic centimeter. And so it doesn't make a huge change in your optical as you go out into your infrared, but in your UV, not only is it changing, because this is in a log on the Y, not only is it changing the level of your continuum, but it's changing the slope of your nebular continuum considerably. This has to be added together with the stars, but your nebular continuum in conditions that are strong can be up to 40% of your total continuum. So this is going to start to change your shape significantly in the UV, and so you have to understand this if you're going to do correct modeling and interpretation. Okay, yeah, put one more plot. I already said this, but just adding it together with the stars. And so this is just showing you from Nell Byler's work back in 2017, if we have a 1,000,000-year-old stellar population versus a 5,000,000-year-old stellar population, where you have kind of a generic continuum from just your stars in the dotted lines, and then you add your nebular continuum to create the full spectrum with the solid lines, you'll notice that there's a much bigger jump adding the nebular continuum in the really young star formation, so it makes a bigger contribution. And so these really young regions that sometimes have the most beautiful extreme spectra that we see, they're going to have more nebular emission lines and continuum contributed to them, and so you have to understand how that all adds together. Okay, and then this last little, I think this is the last time I put up significant equations here, but it's a really important point. So the two types of emission lines that we observe are combination lines and collisionally excited lines have different dependencies. So recombinations, electrons coming back in, then it's cascading down, spontaneous emission to give you these emission lines. But both emission in their equations for the intensity you observe have a density squared effect. So the electron density times the density of the ion you're observing. So that means if you're in the low density limit, which is typical of the local universe, that's fine. But as we start to go to more extreme environments with higher redshift, we really care about how the density affects our lines. And then your combination lines are only going to scale about 1 over the temperature. And so if I have an oxygen recombination line and a hydrogen recombination line, beautiful. The temperature sensitivity cancels out, and I really am just measuring the abundance. Our collisionally excited lines, this actually requires collisions, right? It requires, you've already created your ion, let's say doubly ionized oxygen. It is colliding with an electron to excite one of its own electrons to an excited state, and then it spontaneously will emit again. And so that means we care about the velocity distribution of the electrons. You're going to have a Maxwell-Boltzmann distribution of electrons. So we start to get this E to an exponential term, our E to the minus the energy difference divided by KT, the temperature of your electrons. Okay, so we're exponentially sensitive for our collisionally excited lines to the temperature. That's very important. We still have our density squared component as well. Our collision excited lines are also really, really important because they dominate our cooling of our nebula in most typical conditions. And so that's one of the reasons that they're most strong. They're giving off all this energy. And that means they are going to be the strongest when our temperature is high. And we will go on from there. Okay, so to actually calculate our abundances, I just told you about those collisionally excited lines. So if I measure a temperature and I measure a density of a given region, then that emission line that I'm observing, the only other thing it depends on is how many ions are emitting. Okay, I took out the other dependencies. It only depends on number of ions, temperature, and density. If I measure the other two, I measure how many of those ions are there. So if I actually measure all the relevant ions in a region, let's say I measure the neutral oxygen, the singly ionized oxygen, the doubly ionized oxygen, and the triply ionized oxygen. I measure all of them. All I have to do is add them together. I obviously have to like take the log and add 12, right, to actually get how we put that in our normal terms. But if I do that, I've measured everything. Perfect, easy. But each one of those ions comes from a different zone. I like to think of like a classic onion zone, right, where you have high ionization gas, less high ionization gas, until you go to neutral. And you want to actually characterize the conditions in each one of those ionization zones. Historically, this has been done with what we call a 2 or 3 zone model, depending on exactly what you're doing. Our low ionization zone starts at, obviously wherever we're ionizing hydrogen, around 13.6 eV. We typically define it with nitrogen plus, so it goes from about 15 up to around 30, and this gives us a nice diagnostic in the optical for the temperature. We can use sulfur plus for our density. Then we have an intermediate ionization zone that we typically define with doubly ionized sulfur. There's a nice temperature diagnostic in the optical we can use. Density gets a little bit more tricky, but carbon-3 at least overlaps with sulfur-3. And then we have our high ionization zone, which is classically defined by our doubly ionized oxygen. We can get a temperature from that, and then we have to try to find a density, which again can be a little bit more difficult. You can use argon-4 in the optical. You can use chlorine-3 is a better, I guess, intermediate ionization diagnostic. Where is my nitrogen? Nitrogen-4, which you can see just peeking out here, can give you a density in the UV. So that becomes challenging. And then in low red and high redshift, there's been a long-standing problem of actually measuring really high ionization lines. So, people have been like really trying to understand where helium-2 comes from, like since the 90s, like in detail in nearby blue compact dwarf galaxies. And so this is helium plus 2 because remember this is recombination. So we already have to doubly ionize helium and it'll recombine to give us our helium-2 emission. But we do see all these other things in some nearby extreme dwarf galaxies and as well at high redshift. So we start to see things like iron-5, argon-4. We see neon-3 for sure, nitrogen-4, oxygen-4, carbon-4. We see all these lines. I guess one quick note in case you're not used to looking at this that I forgot to mention is there's a difference between your atomic your ionic and your spectroscopic notation. So when I say like H1, with the Roman numeral, that's like H to the 0, right? Neutral hydrogen. And if I say H2 with 2 Roman numerals, ionized hydrogen, that's H to the plus. So they're kind of one off from each other. Does that make sense? Yeah? Everyone awake? Okay. All right, so I really like to look at Grotrian diagrams. This, of course, can't really be called a Grotrian diagram because it's not the full thing, but a portion of it, let's say. So how do we measure our temperatures? Remember, our collisionally excited lines have this exponential dependence, so we really need to measure the temperature. If I measure a diagnostic from one ion, then I don't have to worry about the relative ionic abundances, right? I can just measure the temperature. So the classical way to do this with doubly ionized oxygen is to measure 5007, this transition right here, relative to 4363. And what you hopefully notice is that these two lines originate from very different energies. That difference in energy is what gives you the sensitivity to temperature. So people will always call 4363 the temperature sensitive line, but it's really the ratio. And that means I could actually use the ratio of any two of these. I could use 1666 relative to 4363. Or 1666 in the UV relative to 5007 as long as my calibration was good. Okay? Same thing with any of these other ions. You notice they have similar structures. In the optical, we often use 5755 relative to 6583 for a low ionization temperature, and 6312 from doubly ionized sulfur to one or both of these redder optical lines to get an intermediate ionization zone temperature. Now, I like to mention that the UV lines actually, as you just saw from 1666, come from much higher energies. They require higher excitation energies. Remember, they're colliding with electrons to excite them to a higher energy level. So just to produce them, I need a lot more energy just to excite them. And so even these commonly seen carbon-3 lines, 1907, 1909, they're going to come from this higher energy level. Nitrogen-3, we're up at 7 eV. Oxygen-3 also up at 7 eV. Nitrogen-4 up around 8. And so if you look at this diagram on the right, if we just look at, an electron probability distribution for a temperature of 15,000 Kelvin, which is pretty typical for a low metallicity region, you see that the energy needed to excite 5007 is like not that crazy. There's a good tail of electrons there that will do it. It's pretty easy to excite. 4363 requires a higher temperature, so we're already in the tail. And that means that if you had a lower temperature of gas, you're just not going to really see 4363. You're not going to excite it. Even if that ionized gas exists, you're not going to excite that emission line. And as we go into the ultraviolet lines that require even higher energies, we're really getting into the tail of this distribution. 1666 starts there, nitrogen-3 around the same area, and nitrogen-4 in the very extreme. So we really have to understand not just the ionization energies, but we have to understand the excitation energies of these diagnostics. Well, we don't usually measure the temperatures in all the ionization zones, even if you have good enough spectra to do a direct method metallicity. And so then we have to use what we call temperature-temperature relationships. They have been measured both empirically as well as from photonization models. And so what you're seeing here is the comparison of a bunch of H2 regions from some nearby spiral galaxies from the CHAOS project. And you can see that the sulfur-3 versus nitrogen-2 temperatures that we measure in these galaxies are pretty tight for sulfur-3 and nitrogen-2. But when we compare sulfur-3 to oxygen-3, we get a little bit more scatter. In comparison, there's a bunch of lines on here. The red one is from photoionization models, and they seem to do a pretty good job. So this tells us that if you measure one of these, you can then, with some uncertainty, predict the other ionization zone temperatures to move yourself forward. Unfortunately, we don't have that same opportunity with density. It's a little bit more complicated. So just a quick summary, because I think temperature is really important. We have our density is going to really start playing a role in affecting these emission lines, because as I said, they have a density squared sensitivity. And I haven't talked about critical density much yet, but critical density is when your spontaneous emission becomes equal with collisional de-excitation. You now have such a high density that you're not just staying in your excited state and spontaneously decaying, you're actually running into other electrons that are causing you to de-excite. And when that happens, you don't get the emission of a photon because you gave your energy to that other electron. And so this can suppress our emission lines and affect the diagnostics we use. Our ionizing radiation field is obviously going to really affect what we see overall because it sets up these different ionization zones. obviously, of what we're going to observe. And then, this excess energy is also going to help determine what the energy of our gas is, the thermal energy. The elemental abundances are going to determine the amount of metals that even cool our gas. So if we have fewer metals to emit, then we're going to have a hotter nebula because it can't get rid of its heat. So we get this inverse metallicity versus temperature relationship. And then dust is also going to end up being important because it modifies the radiation field and causes other second order effects that we'll talk about later, just as like locking up some of those metals that we care about in dust so we don't see them. For our density diagnostics, we can look at a similar diagram, but the first thing you'll notice is now we're looking at ratios of emission lines that come from very similar starting energy levels. That means that they don't depend very much on the temperature because they have a similar energy that they have to excite to, same temperature dependence. But as I was talking about critical density, the two different levels will have these different critical densities that cause them to start to decay, start to collisionally excite at different densities. So if you have one transition, your upper transition to zero, two to zero line that looks like this, and I take it as a ratio with my 1 to 0 line like this, I get an overall trend that kind of does this little zigzag. And this linear kind of curve in the middle is where we want to be if we're going to actually measure the density. We're not very sensitive at what we call the low density limit, and we're not very sensitive at the high density limit. This is the range I like to use for density sensitivity. It's a little bit conservative compared to what some other people use, but if you take about 0.1 times the critical density of your upper level and 10 times the critical density of your lower level, that'll give you kind of a range of what you're sensitive to that you can use your density over. And then this becomes really important. These are all of the density diagnostics that I've been using as of late. There's probably other obscure ones that people doing planetary nebula or symbiotic stars or something use or something like that to get crazy spectra. But you can see, first of all, that the different lines obviously correspond to different ionization potentials. So we're probing different gas. But they also have very different density sensitivities. Okay, so this can be kind of challenging sometimes because if I'm measuring like my sulfur 2 line, which is only sensitive, from a few hundred to, maybe 10,000-ish, and I'm trying to compare it to like a nitrogen 4 diagnostic in yellow that starts at that like 10,000 range and goes to very high, we can't directly compare them, right? That's really challenging to do because they're not sensitive to the same density regime. We can still do like upper limits or something like that, but it's not quite the same thing. Okay, so I wanted to show you just a little demonstration of how this plays out when we look at our emission lines. So this is just like theoretical, if I change temperature and density, how much will a line emit? Okay, it's just like a Python PyNeb emissivity calculation. But what I want you to watch are these strong optical lines here. We're going to increase the density and watch how it changes our line ratio, our temperature sensitive line ratio, and the temperature we get out. So oxygen 3 has a critical density right around 8 times 10 to the 5th. But even at 10 to the 4th, it starts to have a small change. And at 10 to the 5th, it starts to have a big change of what we see. And this then bias the temperature we measure. So you see it starts to drop. It drops a lot, drops a lot. The 4363 has a much higher critical density, and so it's not going to drop until later. And so you can see temperature goes up, goes crazy high, and then it's out of the calibration range. And so in the low density limit of most nearby galaxies, we can just assume a density of 100 and we get a nice temperature. But if you're in a more extreme condition, which we think might be happening in some of our local extreme emission line galaxies, or definitely we're measuring at higher redshifts, we need to include this in our calculations. I'm not going to say a lot about this, but the other thing that I hope is obvious is that if you don't measure all the ions for a given element, you're missing some, right? So you have to do what we call an ionization correction factor. So this is just an example for carbon and oxygen. We have an oxygen ionization fraction and a carbon ionization fraction. These are from photonization models as a function of ionization parameter. And so you can see that doubly ionized oxygen dominates most of our nebula. Singly ionized oxygen is more important at low ionizations. Neutral oxygen also becomes important at low ionizations, and then the photonization models for standard stars don't predict much triply ionized oxygen, but we do see it from harder sources. And you get a similar sort of trend from carbon. Okay, so when you take the ratio of those things, so I say I measure carbon-3 and oxygen-3, and I want to know what parts I'm missing, I take the fraction relative to their totals so I can get out the total, and we get these trends. Okay, so the 1-to-1 line is right through here. So at low ionization parameters, we need to multiply by this to get what we're missing. We're kind of like overestimating what we're getting. And then if we have really high ionization parameters, we're missing a lot of the high ionization gas, and so we need to multiply by those positive numbers. Okay, finally, one of the things that IFUs have been really important for is that for a long time, the way we measured metallicities in galaxies were either just to take one characteristic metallicity of a galaxy, or to try to measure it in a few regions and understand what's going on. And this is obviously a problem because galaxies don't look like this. They don't look like one uniform blue abundance, if you will. For our dwarf galaxies, we get different enrichment patterns spatially, or we get what we call fluctuations in our conditions, our temperatures, densities, and abundances that depend on the galaxy. Some of them are pretty well mixed, some of them are not. In spiral galaxies, they're known to have these gradients, having much higher metallicities at the center and lower metallicities throughout, but there might be some azimuthal variations or maybe variations between inner disk and in the disk. And what things like the Sloan Digital Sky Survey did was just point the fiber at the center. And so we're just taking the average of whatever the abundance is at the center, which was a huge advancement at the time to just even characterize so many galaxies. But what does that actually mean for that galaxy? What if its gradient, what if different galaxies have different steepnesses of their gradients? How are we being biased? Or what do things look like throughout that galaxy? So this, one other caveat that I wanted to mention is that atomic data is also really important. Sometimes we like to think that surely we must know what everything looks like in the laboratory, but things are still changing. And so when I did this paper back in 2015, there had been some updates, some huge updates to atomic data in 2012. So just as a reminder, like some of you I know are using like strong line calibrations from 2004, 2006, some of the older strong line calibrations that were using old atomic data. You're going to get different results than if you use a calibration that has used more recent atomic data. So what I did in 2015 when I was a graduate student like you is I calculated temperatures using old and new atomic data, the new recommendations from a Stasinska 2012 paper, and saw that there were some really big differences at the time in the O2 data and the sulfur-3 data. Okay, that the oxygen-3 and nitrogen-2 at those times looked okay, but it caused big differences in the temperatures I was measuring for certain things. And you might think, well, I'm not using sulfur-3. Well, the most recent release of Cloudy had changes in the hydrogen wavelengths, okay? And the iron atomic data changed a lot as well. So just check, okay? Check whatever you're looking at to make sure you're using the most updated relevant stuff that's right for you, or that you're comparing to things that used similar atomic data to you. Okay, so the local advantage, there's a couple of them. First, we have really nice spectral resolution in some of our telescopes that we use to do nearby galaxies. This is showing you Hubble Cosmic Origin Spectrograph, COS, so UV spectroscopy of a sample of 45 nearby galaxies. It's called the Galaxies survey. It was really just like a service mode survey. We took all the best spectra that existed in the archive and we filled in the holes so you had full spectra from 1200 to 2000 angstroms. And you see a ton of variations here, but this atlas has like good signal to noise in the continuum, greater than 5 in every galaxy, and it has a spectral resolution of 15,000 across the full wavelength range. And so this allows us to do really detailed things that we hadn't done before. And so the spectral resolution that we can afford on the ground and in higher energies is really wonderful. When we go to higher redshifts, I don't know if you know this, but like things blow up with wavelength, so it gets really harder to build those same types of details in like infrared. And then obviously, still staying on our signal noise and spectral resolution, this is just to show you an example of the detail we get from low resolution spectra of this galaxy from the International Ultraviolet Explorer, a previous UV telescope. So if you look at things like the gray that you got for carbon-4 before versus now getting these double emission line P Cygni profiles, you get this absorption here and the emission. It just looks so different. Like the amount of detail we can get with high signal noise and high spectral resolution in nearby galaxies, also because they're closer and brighter, is really incredible, right? And then the spatial resolution. So, you know, JWST has been doing amazing things as well. Their high redshift spatial resolution is something we never really even dreamed of. I think it's incredible. But if you start to look at the detail that we can get in a galaxy like this is like a little dwarf galaxy. That's amazing. We can't match that at high redshift unless we get a really giant telescope in space someday. So this is just showing you a demonstration. This is H alpha emission across, again, about a 10% solar metal poor local galaxy. When we look at kind of like just the flux or the surface brightness, that's like our 0th moment. So we see the spatial distribution of this emission. This kind of data is also really powerful because we can do it in all the different emission lines. So we can start to look at different ionization structures. So like how H beta maps versus our high ionization gas versus our low ionization gas. And you see different portions fill in and different portions are bright. You can start to pinpoint, you can do the continuum and pinpoint where the stars are coming from. And so this tells us a lot. You can do line ratio maps, right, to start doing abundances and conditions and lots of really awesome work. Then we can start to look at the kinematics if we have good enough spectral resolution. So our first order map, we can look at the velocity of how those lines shift away from like a central systemic velocity. And so this is only along the line of sight, of course, but it's telling you about the bulk motion of the gas. So like here, we see nice ordered rotation from the way the velocities are moving. We get our galactic rotation here. But if you see abnormal things, you can trace outflows and inflows and different bulk motions of your gas here. Then you can also start to look at the velocity dispersion of your gas. You can start to look at the line width and how that changes across your galaxy. And so this is going to start to tell you about things like, you know, anything that brought non-thermal motions in your gas, shocks that you're seeing spreading throughout. And so we can get a ton of information. I'm like, why isn't every detector an IFU detector, right? Look at all this information you got. You can still take a picture. You can stop in one frame and take a picture. I like wish everything was an IFU. It's beautiful. Okay. So I'm going to pause because I just threw a lot of technical information at you. And it's okay if you don't have any questions, but do you have any questions? There are no stupid questions. Did that all make sense to you? You're all experts. It's just a review of your grad ISM class. Now you know everything. You could teach it. The atomic database? Yeah, I mean, I think that, yeah, I mean, you know, levels of precision and what we care about are how important they are. I think, yeah, there's a lot of like, you know, are quantum effects included? Are they not? To what precision? Those things are areas that still improvements can be made. And then, of course, the more complicated elements, things that have more electrons, things that have more levels, it takes more to calculate those things up to higher levels. So if you're doing like hydrogen transitions, overall, we feel pretty good about those, right? But as we look at things like iron or more complicated elements, yeah, I think we still expect a lot of changes. And maybe we didn't always think we could measure all those things, but we are getting better and better data all the time, and we're starting to care.
What's the timescales for mixing the difference of metallicity in a galaxy, and whether the timescales are different in rotation and
Yeah.
in radius?
Yeah, so the question, I think you Mike wasn't picking up right away, but mixing timescales, right? So I'm not an expert on that. I usually defer to like Mark Krumholtz when I talk about mixing timescales. But an average number that I adopt, because it depends on many things, but an average number that I typically adopt from things like that are like, it can mix into your local gas pretty quickly, like 10 to the 4 years. But if you have a big galaxy, how long it takes to like uniform things out and mix it in can be, then you're talking about the time scale of your rotation and things like that. So then it can be much longer.
Any more questions?
Thank you for the first part. You show some spectra in the UV visible range, and especially the UV, near UV and far UV. I'm really interested in the absorption features in this spectral range. Are there many data available in this range?
Yeah, the UV is super rich with absorption features, and depending on which ones you care about, there can be even more as you go into the extreme UV, which we have a hard time detecting at the moment. Each regime comes with its own complications. So while you can get really beautiful things like, carbon-2 and carbon-4 absorption, carbon-2 often saturates, right? You get really easy oxygen-1 absorption, but you have to do an ionization correction factor for all the other states. You get silicon-2 and silicon-4. You get your tons of iron lines. There are some weak nitrogen-1 lines. You get a lot of the low ionization and neutral gas lines there, and there's a ton of them. But you also need pretty good resolution to be able to see all of them as well. So, but yeah, it's rich with them. It's beautiful. It's fantastic. You can do a lot with them. It's a lot of fun.
All right, I think you
good for now?
Yeah.
Okay. All right. So this was just a quick reminder of the diagnostic methods we use then to measure abundances of some of the things I've told you. And you'll notice kind of a trend. So when we talk about how sensitive we are to excitation temperatures in the UV, we need very high energies for excitation temperatures. Our optical are more moderate, and our mid-infrared lines are low. For our critical densities, the UV emission lines tend to have higher critical densities. The optical lines tend to have more moderate critical densities. The mid-infrared lines tend to have very low critical densities, and so on. So you can review these in your notes, but I wanted you to have just kind of like a little summary. Utility for UV lines. We use it a lot for radiation hardness, our ionization, because we can just even see our spectral slope. We can do some ionization densities there, escape of ionizing radiation, relative abundances. I'm referring to emission lines here. You can do a lot more abundances with absorption lines. In the optical, we're going to do, again, ionization, temperature, density, dust attenuation from our Balmer lines, total and relative abundances. And then mid-infrared is, sometimes we're worried about we might be seeing gas in different physical areas of our galaxies because we can physically penetrate deeper through the dust. And so we might not be seeing the same thing in the optical and UV. It might be obscured. But we start to see some of these regularly observed low and high ionization species. We trace our warm molecular gas and our pHs. So powerful to put them all together. Okay, so I told you about direct abundances, which is what I love to do, but there is a huge utility in strong line abundances where we can just use some really bright lines over a large sample of galaxies, correlate them with abundances, and get something like this. Metallicity of oxygen on our y-axis and our stellar mass on the x-axis. So this is the famous mass-metallicity relationship, one of the earlier SDSS from Tremonti 2004, where, after you put close to 1 million galaxies on a plot, really nice statistics to do a trend like this. There is utility in trying to understand overall samples of things with strong lines. Now, one of the things I like to warn people, because people will often, this is one of my favorite papers for strong lines still, Cooley and Ellison 2008, is if you look at the dispersion of a bunch of different strong line methods, you're like, that's not that bad. 0.1, 0.2. But look at the differences in the offsets and the slopes. Some of them won't even order your galaxies in the same order if you're using different strong line abundances. So I'm not trying to tell you that you can't use them, But you have to be careful that you're like not combining a whole bunch of different strong line abundances, right? Because then you're not actually comparing the same things. So try to pick one to analyze your whole sample over so that you start to get what that overall profile looks like of your sample. Okay, so the mass metallicity relationship, one of the most powerful things we use to characterize galaxies in an evolutionary sequence in a couple different ways. So first of all, we have our lowest mass galaxies are our little tiny lowest mass galaxies. And we get a little bit more complicated as we get to dwarf irregulars, but we get bigger spiral galaxies and then to our ellipticals. So in some ways, this isn't perhaps an evolutionary sequence for some galaxies in themselves. If they collide a bunch, form bigger things, keep accreting gas. But we can also look at this at different epochs. Here I'm showing you a direct method metallicity relationship I did in 2012 for the local volume legacy. And this is compared to a pretty local relationship from Cooley and Ellison using strong line abundances for more massive galaxies. And you see that there is an offset. So of course, what shapes this? First, star formation in general. As we make more stars, we're obviously going to increase on here, and we'll make more metals, and so we'll increase on here. So we kind of just go up along our relationship with formation. We can also have pristine inflows. Those might initially dilute your gas, but that can also trigger new star formation, causing us to go up diagonally again. If we have a lot of enriched outflows, so you might actually preferentially lose oxygen from your galaxy, okay? Because your supernova could kick out a bunch of oxygen and maybe entrain some of the gas, but that's still the same abundance pattern, and kick it out. And so you would have increased how many stars you have in your galaxy, but you wouldn't necessarily increase your oxygen abundance relative to hydrogen. And then finally, as I mentioned, we tried to look at how this evolves with different epochs. So are we seeing an evolution as we go up to, redshift 2 to 3 here? Well, again, these aren't necessarily all the same methods, so understanding the offset is really challenging. If we look sometimes at stacks where you kind of average over a lot of differences, like the MOSDEF study did for redshift 2 to 3 galaxies in 2021, you get a relationship that has much smaller evolution from redshifts 2 to 3 and looks much more like my redshift 0 trend. So again, this is just kind of telling you, like, we have to be really careful in what we're comparing. Okay, and then, there's a lot of promise for this going forward, or, reasons we want to do this better and better, because cosmological simulations make, and, semi-analytical models make a lot of different predictions for what the mass metallicity relationship should look like. And in particular, the amount of feedback tends to really change what the slope looks like and what the overall offset is. And in fact, it looks even more stark if you start to look at the actual slope of those different models as a function of redshift. You get quite a big difference. Like, is the slope increasing as you go to lower redshift? Is the slope decreasing as you go to lower redshift? Like, it's like very, very different. And JWST is going to be really exciting in the coming years because there's a bunch of programs doing like large numbers, and I'm sure I'm missing some of them. There's always new things happening with JWST all the time. So if you have a favorite program, please let me know what I'm missing. But that are doing large statistics, redshifts 2 and 3 and even higher, that are going to do direct abundances and really measure these things really well. So we're excited about that. And, I never in my wildest dreams thought JWST would start measuring these faint 4363 lines that we need to measure temperatures at redshifts, 7.4, 8.9, things like, 4.26, I said the wrong ones, 9.11. Like, that's crazy. That's really, really far away. We're looking at light, from more than 10 billion years ago traveling to us, and we're measuring the temperature of the gas. That's crazy. So this is really, really exciting, but it requires, and many teams have been doing this, but it requires really detailed, deep spectra. And so above redshift 6, we only still have about 10 of these that have significant metallicity with the direct method detected. And so it's still really hard to tell what the evolution is. If you look at some of these different plots that have been made, like, there's lots of different points on here from redshift 2 to 7, and trying to understand statistically how you separate those is really hard still. We need more numbers of these, and they're coming. We're going to get looking forward. Okay, and so I wanted to mention that another thing we do to try to understand our gas is compare it to the stars. Like, are we seeing the same thing? Massive stars should have formed recently from the gas. They should have the same abundances in them prior to a lot of mixing or further chemical evolution as the gas that they formed from. So when we look at things like the stellar mass versus the stellar metallicity of lots of different galaxies, where the red and blue points here are measured from red and blue supergiants in the nearby universe, we can compare that to what we measure from the gas. And what some people have found that do these in details, like Fabio Breslin's work in 2022, is that if we take the difference in the metallicity of the stars and the gas, that there's obviously variation here, but it's not as bad as you might think. And our collisionally excited lines, that temperature method that we use, does a pretty good job at lower metallicity. It agrees with the stars really well. And that's where we can measure it better as well. That's where the gas is hotter. That's where those lines are more significant. And then as we start to go to higher metallicities, we start to see the recombination lines start to become really low uncertainties. They start to agree with the stars really, really well. And so that might be a better method if you can measure it at higher metallicities. But people are always like, we don't know anything about metallicities. We're doing a pretty good job when we do it in detail, where it's not so bad. Now going back and comparing on this plot, is there evolution in our stellar work? Well, some trends like Kashino 2022 have found that at redshifts higher, like redshift 3, or the Cullen 2019 points are on here from redshift 2.5 to 5, that we're seeing an offset from our redshift 0 to our higher redshift stellar MZR. But this also depends on how exactly we're measuring everything, I guess. So one of the things we do is to try to understand what our stellar mass is we'll run these different models. And we tend to find, if we're using constant star formation history in some of these things, that we always see this offset between what we measure in the gas and the stars, even at higher redshifts or just at low redshifts. And then in GISM 2019, did a different work, started looking at both redshift 0 galaxies in blue, and then Megasaura is around redshifts 1 to 3, and the Steidel points from 2016, and measured it with linear combinations of bursts. So you get a luminosity-weighted age and metallicity, and then you can add everything together, and you start to see that the properties that you get from both the gas and the stars, there is some scatter, but they start to line up really well on average as a whole. And so we have to be careful in what kind of star formation histories we're assuming when we do this kind of work. And then, of course, coming back to our strongline abundances and understanding if they're evolving. So here is some nice work where we're looking at this kind of new parameter that's using both R2, so like oxygen 2 and our oxygen 3 versus measured oxygen abundance. This is for a bunch of those JWST, higher redshift points. And then this is from, again, another large compilation. So redshift 1.4 to 3.7 from ground base, redshift 4 to 9 with JWST. Yeah, all the way up to redshift 9. And you'll see that the lower redshift points, like on this plot, for instance, kind of offset from here. And so there's been a lot of work recently to try to recalibrate these higher redshift strongline calibrations. But there's one part here that's still been largely missing. Not every work is missing this, but I just want to say it's something we need to take care about. And that is how the density plays a role in these stronglines. So I mentioned that we're starting to care more about density being higher at higher redshifts. There are direct measurements in a handful of the very brightest galaxies at high redshifts that are showing densities in excess of 10 to the 6. Okay? And so we care about, maybe not in every high redshift system, but in the ones that are most extreme, we need to understand what we're seeing. And so this is showing you two strongline ratios, O32 and R23, that what they look like from photonization models, with a bunch of different things, different stellar ages and different metallicities and different things like that. But the overall population of the models for a gas density of 100 versus a gas density of 1,000,000, they occupy different places on this diagnostic diagram. So that tells us that we can't just recalibrate at high redshift. We have to also add another knob on that diagnostic, which is density. Okay, so, and do we really care? Well, even at low redshift, okay, classy is basically redshift 0, like 0.009 and stuff like that. So galaxies that are really in our backyard. Matilda Mangazi looked at a bunch of different diagnostics. So sulfur 2 is the classic optical diagnostic that characterizes the low ionization gas, and you typically get low densities. They're also sensitive to low densities, but it does go up to about 10,000 for sensitivity, up to about here, and we don't really have points up there. Then we have these UV line diagnostics, carbon-3, silicon-3, and nitrogen-4, which probe higher ionizations, with nitrogen-4 being the highest. And you see, even though they're sensitive to higher ones, they're also not hitting, for most of them, their lower limits. Some of them are, but there's a bunch of points that are well measured in this higher density regime of a few 10,000 up to 10 to the 5th, even in local galaxies, telling us that we are actually seeing some density stratification that we need to actually consider in our whole picture of how we analyze these galaxies. And then recently, by several groups, some of them listed here, this has also been looked at as an evolution in redshift. So sulfur 2 or oxygen 2 that are measured from the optical, these low ionization density diagnostics, again, they start 10 to 100 on average at redshift 0, and they evolve to higher densities to being around 1,000 or so on average at the highest redshifts from measurements. And then we can start to see Michael Topping did some work from the Aurora survey using carbon-3. This dashed line here, these are just very typical galaxies that go up to higher redshifts, and these are already more than an order of magnitude higher than the low ionization. That's a more intermediate ionization diagnostic. And then Zoraida Martinez recently was doing this with both carbon-3 and nitrogen-4 for more extreme galaxies from the literature, and nitrogen-4 goes even higher, but we still see this overall shape. And so it seems like density not only is higher in high ionization zones, but it's evolving with redshift as well. And this probably makes some sense because the universe evolves. So we expect to see that. But I just want to point out that this will also bias everything else you measure. Okay, so we talked about the critical density of 5,007. So for 4363 to 5,007, if I assume a low density of 100, these are the types of temperatures I'm going to get. This is from a sample of galaxies that had carbon-3 and nitrogen-4 measurements. And if instead we use their higher density measurements in the temperature calculation, you get these lower temperatures. So you see, we started to get some of these temperatures that were beyond the hydrogen cooling limit, past 30,000 Kelvin, that just shouldn't be physically possible in an H2 region. And it turns out, if you include the density that you actually you can measure, you get lower temperatures. Okay, so this is important to do. And then Matt Hayes, in a recent work, took a bunch of stacks of all the high redshift JWST data. I think Emma showed this plot as well. It's a fun one. And the real takeaway here, I haven't talked about nitrogen or oxygen, but Emma did, is that if you assume a density of 10 to the 2.4, you get an oxygen abundance here. But if your density was actually 10 to the 6, your oxygen abundance would be much higher. And so you're going to measure the wrong abundance if you don't get all of your conditions in the ISM correct. And like I was saying, I think this makes a lot of sense in terms of just the overall evolution of the ISM over redshift. And so this 2024 work is showing you points in blue at redshift 0 up to redshift 5 in red. And we're now looking at the surface density of the star formation rate, just overall surface density versus of the gas, okay? And so you can see that there's this, obviously a lot of scatter, but increasing trend, and different depletion times on here as well. But the lower redshift galaxies live down here, and they're real close to this like blue dash line here, but they seem to become more steep at higher redshift. And so we're getting these evolving gas conditions. Our dark matter virial halo densities are going to be higher. We think that evolves as 1 plus redshift to the third. So we have much, much more compact, dense regions that are creating a lot of gas that are causing these higher surface densities of gas that lead to higher surface densities of star formation rates. So that all makes a lot of sense. And in turn, this is going to lead to other parameters that correlate with the surface density of the star formation rate, such as the ionization parameter that we measure from the gas. And so Naveen Reddy last year as well also measured this trend with a bunch of different data from different redshifts and found that as you get to these more extreme surface densities, you're also increasing your ionization parameter a lot. So our gas density, our ISM pressure, they seem really, really important. They're the key things really in setting the conditions in our galaxies across cosmic time. Okay, a few notes about dust, which I am not an expert in, and you have more lectures in this course about dust, but it's really important to our interpretations, so I'll say a few things here. First of all, things like oxygen, carbon, silicon, obviously iron, these things deplete onto dust. And so whatever I'm measuring from the gas is not the full picture if I don't know what has been depleted into dust. It's not giving me my total abundance. And so this is really important for us to understand if we really want to know what abundances we're looking at. And I'll just mention that I think, I'm sure there's a rich history that goes back many, many decades before this, but a really seminal work from Ed Jenkins in 2009 was to look at 243 sight lines using UV absorption to all these different stars in our own Milky Way and compare it to the reference solar abundance pattern. So he did the entire abundance pattern. He measured a lot of different elements and looked at how they were depleted as a whole and started to try to understand what that meant for the different depletions from the gas. He found some surprising things. In particular, he uses this overall depletion F star thing. Again, that's the average of everything together, and found that some elements, if you got to high enough column densities, actually started to deplete, even though they had previously thought to not do so. So it was interesting. But this work has been greatly expanded by several people. I know Annie's done work on this. I'm going to highlight Julia Roman Duvall's work on this recently, now expanding this to lower metallicities in the LMC and the SMC down to 50% and 20% solar. And first of all, these plots are just kind of pretty to look at, but what you're seeing is that as we go into increasing column density, you're seeing the fraction of the dust that's contributed by a different element by color. And so if you just kind of like almost let your eyes glaze over and just look at how the shapes of things change, looking at high metallicity Milky Way to the Large Magellanic Cloud at 50% solar, to the Small Magellanic Cloud at 20% solar, you'll see that things really change. And one of the things that was impressive to me to see were things like oxygen and silicon started to take more higher and higher column densities before they really contributed anything to the dust, before they really started depleting significantly. And you can also see that the fraction of the metal in the dust versus metallicity here with these different measurements for different elements by that same color coding, or the overall dust to metals in red here. And you see that it's changing as a fraction of metallicity. It's not staying constant. You can't just assume one of these dust to metals ratio. Work overall, now looking dust to gas and kind of considering our dust to metals as well versus a function of metallicity. What Julia found, I guess, is most important near with metallicity. And so this implies that our grain growth might actually be slower at lower metallicity. I like to measure low metallicity galaxies. This is great news for me. I don't have to worry about the dust as much as I thought I did. But it also means that we need to understand this better for like high redshift environments when we're starting to find metals being injected into galaxies for the first time. And sometimes we're seeing even more dust than we expected. So is it coming from different sources? What is the composition? What is the screen like? Is it uniform? Is it not? These are all things that are going to affect what we see. Okay, so just quick summary of that. These depletion corrections don't follow the Milky Way, we need to understand them at low metallicity, especially for high redshift. We need to understand what is depleting and how much to understand the total gas phase abundances that are in our galaxies, to understand the history of what's happened there. And we have to understand if the composition and the shapes and the sizes, everything like that is changing. This all be really important. Okay. How do we measure dust? Well, in the UV, we can do that by measuring the slope of the continuum, what we call the beta slope, usually measured around 1550 angstroms. And then this is compared to the stellar E of B minus V value, so the overall attenuation in the B band minus the V band, but we extrapolate that by measuring the stellar continuum and fitting models to it and seeing how much attenuation occurred. And we find that the beta slope is actually a really good proxy. This was done for some things that had Lyman continuum escape, so detected Lyman continuum emitters and non-Lyman continuum emitters, but you can see that overall for both types of galaxies, the beta slope acted as a really good proxy for understanding the amount of dust that the stars were seeing. And then when we do this for the nebular gas, we typically do that from the Balmer decrement, the theoretical ratio of the hydrogen Balmer lines to what we observe. And Matilda Mangazi looked at this again for the Classi sample and found that there was a pretty big scatter when we compared what we measured from the gas to what we measured from the stars. You can see here that from the 1-to-1 line, there's quite a bit of dispersion. And so then she also looked at the change in E of B minus V versus the nebular gas, and it seemed to kind of follow a trend. So there's larger deviations from this at higher attenuation values. And this is something she's still trying to understand, but here she's color-coded a small trend, perhaps. I don't know, it looks pretty scattered to me with star formation rate. Okay, I always plan too much and I go over time. So does anyone have an element that they're most interested in hearing about, like carbon, nitrogen, neon, or helium, I think were my choices for you. Nitrogen? Anything else? Carbon, nitrogen, and carbon? Okay. So we're going to skip neon for now and go to nitrogen. Okay. I like to start the basics if you're not familiar with nitrogen. We typically measure N to O versus O over H, and we get this like overall increasing trend. Okay? So we first have this primary plateau. This is just from this means that the amount of hydrogen and helium your star starts with does not, is all that your nitrogen abundance depends on. So you go through just like typical evolution, your star blows up, you get out some nitrogen and oxygen that are always constant. This is your primary plateau, okay? But at some point, you start to build up enough metals in your gas that you can seed the CNO cycle, okay? So you seed this CNO cycle. The bottleneck, the step that takes the most amount of time, is this one here. And while you're left with some nitrogen-14 hanging out, before it can go into the next step, if you have a lot of dredge up in your star, it brings nitrogen-14 to the surface, and your winds blow it out. And so not only do you get an excess of nitrogen in your gas, but you lost some carbon that was consumed in this process and not returned back at the end because you didn't complete the cycle. You kicked the nitrogen out. So you consumed some carbon to produce nitrogen, and you start to get this secondary, which means it depends on the initial metallicity, that's what secondary means, increasing trend here. So we get this overall slope. Okay, well, it can be even more fun and complicated than that due to a couple different reasons. So if we start to consider things like inflows, you could imagine that we might deplete our oxygen relative to hydrogen, getting in pristine gas, but we might not change the relative N to O. And then if we blow up some core collapse supernovae that have a lot of oxygen and we preferentially lose our oxygen, then we might actually go backwards diagonal on this plot. So that can create a lot of scatter. We also have that these elements are typically produced on different time scales. So you often get oxygen enrichment quite quickly, maybe 10 million years from type 2 supernovae is where they peak, and you don't get nitrogen enrichment until a few 100 million years later from your asymptotic giant branch stars. So where you are in your burst cycle will also depend where you live on. So you might have had some really recent star formation and some supernova go off that give you some oxygen abundance into your gas, and that might cause you to go lower. And then later, after your starburst, when your AGB stars are starting to contribute, you might end up with some enrichment in N to O. Okay, well, some of you are like, man, I assume just this one little trend here when I do N to O. Yeah, that makes it challenging because there are time-dependent yields. It also depends on your star formation efficiency and your star formation history. So when people like Chiaki Kobayashi does her overall chemical evolution models, she has to assume, how many stars formed at different times. And so if you had like this lower efficiency here where you didn't have a lot of star formation early in time, you are going to very slowly build things up. So you'll get some oxygen right away, but you're going to get your nitrogen back as well before you really kick up your star formation. So your oxygen, will go up a little bit, but then you'll get your nitrogen enrichment after time, which sets this overall pretty high primary plateau before you've built up enough oxygen to kick off the secondary. If you have a lot of star formation efficiency, a lot of stars are happening, a lot of stars are forming, you're going to get a ton of supernova early. You're going to kick up your oxygen really early on in time. So you're already able to see that CNO cycle. So you already have a ton of oxygen. Your N to O plateau stays pretty low. You kick on your secondary early, and you start to increase that way on the trend. So where that is can also depend, again, on the star formation history, how efficient you were early in time. Okay, and so there's been a real renewed interest. I know that Emma talked about this a bit of this study because we're finding these higher N to O values at high redshift that are very confounding to us. But one of the things I just like to remind everyone is that we're doing this again with our basket of fruit. Okay, so over here, this well-known loved trend is from our low ionization, nitrogen plus, oxygen plus from the optical. These measurements are all coming from ultraviolet high ionization, nitrogen 3 or nitrogen 4 over oxygen 3. And so we're trying to understand a lot of components of this, the primary versus the secondary, the low versus high ionization. Are there supermassive stars at high redshift? What are Wolf-Rayet stars doing? How burstiness are things? What are the duty cycles of this nitrogen enhancement? Are there tidal disruption events? What are shocks doing? What's the environment like? Are these really high density playing a role? What are the effective yields? The population fraction, how common are these galaxies really, or it's just because they're the brightest? What is happening? So again, lots of people are working on this. One study that I know intimately is from Carla Ariana Cordova, who was looking at classy galaxies as well as some of these higher redshift galaxies. And we're seeing some general trends that, again, matches with that overall density evolution I was telling you about, or the compact, high surface densities. So with star formation rate surface density, we're seeing an overall trend of increasing N to O from low to high redshift. It seems like our higher redshift galaxies have higher star formation rate surface densities. And same thing with the stellar mass surface densities, increasing this way as well, with higher redshift galaxies having these higher surface densities. And there's a lot of fun, crazy models that are being put forth to try to explain these things. I've been really enjoying seeing all these papers come out from Devesh Nandal, just a theorist that models these like very massive stars. So you're talking about thousands of solar masses, and you can basically make up whatever you want, right? But it's a lot of fun because you can start to play with how much is ejected versus collapsed, all sorts of different components, and has come up with some of these different models that if you, eject 10% of your total mass or 40% what you get out, and there's some sweet spots in here, maybe around like 4,000 solar masses, where you're getting a lot more nitrogen than you are oxygen. And so this could have a big effect. One of the other models that I really liked came from Kobayashi and Ferrara that looked at the importance of the timing of your star formation. Really exciting, subsequent bursts that involved Wolf-Rayet stars so that you could get this rapid enrichment in your region. And this was really appealing to me because we recently got a really, really deep spectrum. This is not out yet, so I'm just sharing with you some exciting spectra. This is from the GLIMPS survey. So this is a massive cluster that's lensing a bunch of galaxies. It's seeing very, very deep, and they recently got director's discretionary time to get follow-up spectra 40 hours. And so you can see the old UV and part of the optical spectrum that existed before this, and then the new DDT spectrum is incredibly high signal to noise. So this is a redshift 6 galaxy that we're measuring things like argon-4 densities in. Like, what? I didn't think we could do that. But the thing that's really exciting to me is up here. So the helium-2, it's hard to see here, but kinematically when I measure it, it's broadened compared to the other emission lines. And then this overall like little bump thing you see here above the continuum, to me, as someone who studies this looks like a baby Wolf-Rayet bump, where in particular we only see this nitrogen-3 line here when we have things like Wolf-Rayet stars that are there. Otherwise, we don't see that at all. And then there's a bunch of other little emission lines that are hard to know which ones you're seeing because we're not resolving them, so I haven't tried to fit them. But we think we're seeing Wolf-Rayet stars, and this is at redshift 6, which is really, really exciting. They also did this in the Stumbers arc. Emil Rivera Thorson did this and saw Wolf-Rayet features there. And there's been SBS 335-02, one of the most metal poor local galaxies. Wolf-Rayet stars there as well. Okay, so the other advancement here is we have deep enough spectra to measure these weak broad components there. I tried fitting a single broad component. I got a bunch of residuals. Now you all know about Bayesian analysis, right? Bayesian inference criteria didn't do a great job. So I tried to fit 2 broad components. That looked the best. I also tried to fit an exponential profile, which has been recommended recently for really high densities if you have electron scattering. But it does a really nice job. But the best fit statistically was with 2 Gaussians. And so it seems like there's some complex kinematics going there. But when I account for the broad components, when I measure my nitrogen, and how it affects oxygen-3 and H-beta as well. I can measure 3 different nitrogen density or nitrogen to oxygen abundances from the optical and UV, and they start to agree finally. We haven't had a lot of that happening with the optical and UV. They are enhanced, and they agree with the previous measurement for Michael Topping, which is really, really nice. One of the things that's interesting is that the carbon to nitrogen abundance is relatively flat compared to local samples, and when we look at carbon to oxygen, it's very depleted. Some people have suggested that these low C to O's might be the first enrichments from supernova that we're seeing, but I also think it might just be that we're consuming all the carbon in the Wolf-Rayet stars and getting this nitrogen enrichment. So one object, this is by far not the like end all be all, but it's very enticing that we're probably seeing very massive Wolf-Rayet stars in the early universe, which is really exciting to me. And we can start to tell these histories and abundance patterns that we're seeing. I want to mention that Chiaki Kobayashi has a nice 2025 paper doing some of these chemical enrichment models. And so you can see the time scale in gig years, right, is the color coding. And so you very quickly move across these N to O, C to O, and carbon to nitrogen plots, kind of like the ones I just showed you, very quickly move across to get these, enriched nitrogen in these types of, multiple bursts where you have Wolf-Rayet stars. And can also come down to these low carbon to oxygen abundances as well. And so these are some of the high redshift galaxies that they're matching really well with carbon and nitrogen abundances with this model. Okay, I'm going to finish with, because I don't have a ton of time anymore, I want to tell you just a little bit about some cool things with IFU that you might not have seen. So KCWI, MUSE, I would argue those have been the dominant powerhouses recently. They do unbelievable things. And they have different benefits. Like MUSE gives you a much wider field of view that you just will never be able to do with KCWI. KCWI can give you a little bit higher spectral resolution. There's different things you can do, and it's amazing. This is some mapping with KCWI of a nearby galaxy where you're seeing the disk edge on. And so you have the minor axis here and the major axis here. And these different blocks, like outside of the main emission of the galaxy, we're now sensitive enough that we are measuring 4363 in the CGM off the galaxy. And so what's really cool about this, what Alex Cameron was able to do, come on slides, I don't want to change. Okay. Was actually able to do a direct method metallicity map across here. And what you can hopefully see is that there are higher or brighter yellow colors at the top and the bottom here along the minor axis. This is the outflows or ejecta of metals. And there are lower metallicities on the edge of the major disk where we think inflows are accreting into that galaxy and bringing more pristine gas, like directly measuring the baryon cycle and the flow of metals here. In a different way, another study that's done with IFUs, this is IRAS-08, 10 to the 10th solar mass galaxy, obviously seeing this more face on. But this has some really beautiful data. Please. Doesn't want to show you the data. Okay, I give up. I'll show you the results. The IFU data of this shows a couple of things that are really cool. So these are all the points from the galaxy, and these are the points that are measured outside of the galaxy into the CGM, and they're color-coded by in line with H1 arms and outside of the H1 arms, but they end up lying in the same place. But what is crazy is what you're seeing when you look at these different maps of O2, O3, H beta, and we look with distance from the moving from the center of the galaxy out, is that we see this decrease and then this transition to a totally different type of profile. So we're seeing the actual transition in the emission in shape from the ISM to the CGM. And we can also see this in a diagnostic like O32. You see that the slope goes from decreasing to increasing as we start to hit the CGM. That's, to me, really amazing. And then finally, I want to mention that, again, people are doing this at higher redshifts. So this is from the Templates ERS program. And so taking a lensed galaxy like this, that's at redshift 1.3, and actually starting to do some spatially resolved sulfur-2 densities, oxygen-3 temperatures, and direct metallicity abundances. And, you know, it's hard for them. This is where the outside of the contours are where they go below 3 sigma. But within here, you can see even variations where we're measuring real metallicity variations of about 0.6 dex already at this cool redshift. So this is really important for us understanding these variations. And then in this work, Grace Oliver is also looking at how different strongline methods compare. And some of them show more variations than others, but some of them really wash out the details or the variations that we're seeing in the real physical properties of the gas. And then one more work here was looking at, by Eastman 2024, was looking at an integrated metallicity of an H2 region versus spaxel by spaxel metallicities. So the amount of vertical scatter you see kind of shows you how crazy it is, how much variation you actually see, and you're compressing into a single integrated metallicity. And there's a lot of variation here by ionization parameter, that detail that we lose when we go to our integrated metallicity. Okay, so I just want to mention there are a ton of these studies. We've already heard a lot about FANGs this week, and so I hope you continue to look at FANGs, really cool. There's many, many cool IFU studies. I'm not going to be able to mention them all. And I think the final thing I will say to you is that we need to keep building IFUs, and so I worked on a HWO, Habitable Worlds Observatory. Oh my gosh, I don't know what happened here. This is supposed to say Science Case Development Document, DD. That's not what it says. But Beth and James and I submitted one of these, and showing that at higher redshifts in the few areas that we've been able to look at variations in UV carbon-3, we see real variations. And so we want to be able to actually map the variations in the ultraviolet of, you know, escape of ionizing radiation, of the stellar population variations, of the high ionization gas density differences, of the absorption lines, of the CGM emission. We want to be able to map that, right, spatially, and then compare it to the same things that we see with our MUSE IFUs, with our JWST MIRI, and compare all the different spatial variations we see across all those things. And, you know, in a simulation, we can look at different apertures versus a whole galaxy, and we get very different absorption line profiles. We get very different emission line profiles. We're losing a lot of the details kinematically and physically of what's happening. And so I will leave you with some main takeaways of what I think are really important about these different diagnostics, about dust, how excited I am about the future of synergies between different IFU observatories, and yeah, I hope some of you are more interested in doing this work in the future because we need a lot of hands. There's a lot of fun things to do. Thank you.
All right, any questions? Thank you very much for a great lecture. Let's see, who wants to start? Yes.
When you compared the stellar metallicities and the ISM metallicities, so is it a direct comparison, or do you have correction factors to account, for the chemical evolution?
Yeah, so the comparison between the stellar and ISM, the ISM abundances are pretty straightforward. But the part that isn't so straightforward is the stars use this overall template to characterize the metallicity of the star. And then they use an abundance pattern to say what the oxygen abundance is, to compare it to what we measure from the gas. So yeah, making progress on that is really, really complicated because no one has done a suite of stellar atmospheres and evolution for non-solar abundance patterns. So there's a lot of work that to be done on the stellar modeling side still.
Yeah, because people doing that in the Milky Way, they really account for the fact that, the star, formed a few billion years before, so they at the metallicity different, and also that you have freshly formed elements that are, diffused toward the surface. Okay, so you don't do that yet in those galaxies.
Yeah. Lots more to be done.
More questions?
Can you go back to the glimpse survey results? If I heard correctly, you said now UV estimated value and opticals are matching each other also.
They're much closer anyway.
And then consistent with topping measurements.
Yeah.
Well. Would that mean that other galaxies with very high nitrogen, is it real?
I think some of them not as bad as we think because Zoraida has a paper that's submitted. We hope to have it out soon, but some of them slide over in oxygen abundance. And so then they're not so far offset because they're on the secondary trend. And so they're not so crazy anymore. But this one was kind of a funny accident because the extra corrections that we did to the abundance first increased it, but then you account for the broad wings and that reduces your emission line flux in the nitrogen lines. And so it was funny because the double correction actually brought it just pretty back close to where Michael Topping had it. But I would argue that Michael Topping's papers are one of the most careful high redshift analyses that have come out.
I see. Yeah.
So some of them have done varying degrees of different things. Yeah, so the corrections are different for different galaxies, but some of them are high. It's not just this one. There are some of them that are very, very high, and I hope your model maybe is good for many of them, but we should try to get deeper spectra of all of them.
Thank you.
Yeah. Yes, Eileen, a student question. Thank you.
Hi, great talk. It was lovely. I was wondering, I'm really curious about this broad helium-2 emission that you find. What do you think is causing that, the Wolf-Rayet star or something else? I'm curious.
Yes, great question, and something I didn't say. Thanks for bringing that up. Yes, so nebular lines intrinsically are like, on the order of 1s to 10 kilometers per second just from the thermal broadening of the gas. The intrinsic width of a nebular emission line is very, very narrow. And so normally what we see is just the spectral resolution. The broadening of a line like that, like helium-2, we often see from stellar winds. And so either very massive stars, or the Wolf-Rayet stars will characteristically broaden helium-2. The difference is we can see that just from massive or very massive stars. And so seeing the extra nitrogen bump is the thing that tells us that we think that we have Wolf nitrogen stars. You have Wolf nitrogen, Wolf carbon, Wolf oxygen. Some of them look very similar to, they get crazy, but we think these are Wolf nitrogen stars from that combination of the broad helium-2 and the nitrogen-3 line. Yeah, great question.
Any more questions?
If you have a different favorite element, I'm happy to talk offline as well.
Again, great talk. Super cool stuff. Could you talk more fundamentally what the difference between direct lines and strong lines are?
Yeah, so when we say direct method, it really means that we are trying to directly measure the number of ions relative to hydrogen that are there, because we're measuring the temperature and the density. And so the emission line after that just depends on abundance. A strong line calibration is where we've taken, we've measured direct metallicity methods, and we say, how does that correlate with a ratio of strong lines? Right? And so we get a calibration of direct metallicity, and let's say oxygen 2 plus oxygen 3 over H beta is one of the ones that's common. And so we'll plot that on the y-axis, and you get some sort of trend. And so then when you can only measure 5007 and a bright O2 line 3727, you measure that, find where it is on your plot, and you say, that tells me it should have a direct abundance around this. So it's just a either an empirical or a theoretical calibration that predicts the metallicity, whereas the other way we're trying to directly measure it. Yeah.
All right. Any last questions?
So do we have a time evolution, a cosmic evolution of the metallicity?
Of the what part?
Of the metallicity? I mean, the metallicity is increasing, but is
I'm
there
sorry, I'm
first
just not understanding the evolution of.
metallicity?
Oh, the metallicity. Sorry. So this is where I feel like I'm an old curmudgeon, because I will tell you that I don't think we've measured it yet. I don't think we have any direct evidence that is firm of measuring that evolution. That doesn't, to me, tell you, I don't think that it doesn't exist. I think that we've been measuring the brightest things that we can measure at high redshift, and they're generally more massive and more metal enriched. I don't think we've measured the super faint, low metallicity things yet. I just don't think we've done it. I think we will, but I don't think we've done it yet.
I mean, just to quickly follow up on that, I think arguably we've got better constraints on the IgM metallicity at those redshifts, because there you do have the sensitivity to very low values from the Lyman alpha forest.
Which is why it's been modeled for a very long time. Yeah. Good job, CGM and IgM. Yeah. Quasars are so bright. They're so nice. They allow us to probe really far away. What's the highest redshift quasar now? It's like crazy, isn't it? Anyone remember off the top of their head? It's high.
On the note of uncertainty.
Yeah.
Let's thank Danielle once more.